Hello there, and welcome back to Sleep Science Time. I am so glad you've chosen to be here. It truly means the world to me that you would share your quiet time with me as we explore these science journeys together. Before we begin, I'd like to kindly ask you to think about hitting that subscribe button, liking the video, or even just to leave a comment. This helps the channel grow and to allow me to bring more of these videos to you. So, find your most comfortable spot and let's begin. Imagine just for a moment that the world outside your window goes completely dark. Not just the street lights, but every light in every house as far as you can see. The gentle hum of the refrigerator stops. The little red light on the television blinks out. A deep, profound silence falls. What you're left with is the world as it was for almost all of human history. A world without electricity. It's a strange thought, isn't it? We think of electricity as a modern utility, something that comes out of a plug in the wall. But in truth, it is an ancient and fundamental force of nature. It is the lightning that splits the sky in a thunderstorm. It is the tiny, invisible spark that jumps from your fingers on a dry winter's day. It is the very energy that fires the neurons inside your own brain, allowing you to have the thought you're having right now. For most of history, this force was pure magic, a terrifying, beautiful, and completely mysterious power. This story is about the patient, curious, and sometimes downright eccentric people who first dared to catch that lightning in a bottle. The quiet explorers who, through centuries of gentle curiosity, transformed that magic into the calm, predictable servant that now lights our homes. It's the story of an invisible fire, a ghost that lives in the wires of our walls, that powers our dreams, literally, if you dream about your phone charging. And it is a story that starts not with a power station, but with a piece of amber and a curious touch. Our story doesn't begin with a great scientist in a lab, but with the ancient Greeks, thousands of years ago, on a sunny afternoon. They had noticed a quiet little curiosity. If you took a piece of amber, that beautiful fossilized tree resin, and rubbed it with a piece of wool, it would suddenly gain a strange new power. It could attract and pick up light objects, like feathers or bits of straw. To them, this wasn't science, this was magic. They concluded that rubbing the amber must have awakened its inner soul, or as they called it, electron. And right there, in that ancient word for amber, the first seed of the word electricity was planted. For over 2,000 years, this little trick remained just that, a charming piece of parlor magic. It was a footnote in the great book of nature, a strange property of a single, peculiar substance. No one really knew what to make of it. What was this invisible force? This amber soul that could reach out and touch things without contact? The world simply wasn't ready for the answer. It wasn't until the 1600s that an English physician named William Gilbert decided to take this old magic seriously. He was the court physician to Queen Elizabeth I, but his true passion was experimentation. He discovered that it wasn't just amber. Other substances, like diamonds and glass, could also be given this strange attractive power. He was the one who first coined the modern term electricus to describe the effect. Gilbert was the first to treat this invisible force not as magic, but as something that could be studied, catalogued, and understood. He built the very first scientific instrument to detect static charge, and with that, the ghost in the amber was finally brought into the laboratory. The first tentative steps had been taken to transform this ancient mystery into a modern science. But it was still a very, very long way from lighting up our homes. For a long time, the study of electricity was a fleeting and frustrating affair. You could rub some amber, create a tiny spark, and then it was gone. The magic would vanish as quickly as it appeared. The next great challenge, then, was not just to create this invisible force, but to somehow capture and store it. The breakthrough came in the 1740s with the invention of the Leyden jar. It sounds very grand, but it was essentially a glass jar lined with metal foil, with a metal rod sticking out of the top. It was the world's first capacitor, a device that could hold a static charge. And the charge it could hold was significant. For the first time, scientists had a way to bottle this invisible fire. And like anyone who's just been given a new and slightly dangerous toy, they immediately started zapping things with it. This new device turned the study of electricity into a form of public theatre. Scientists and showmen would hold demonstrations where they would charge up a Leyden jar and then deliver a jolt to a chain of people holding hands, making them all jump in unison. It was shocking, it was entertaining, and it was a bit silly, but it was also science. These public displays sparked a massive wave of popular interest in this mysterious force. The Leyden jar was more than just a party trick, though. It was a crucial tool. It allowed scientists to accumulate a powerful enough charge to conduct serious experiments. It changed electricity from a momentary spark into a force that could be held, studied, and, for the very first time, controlled. The ghost was no longer just in the amber. It was now in a bottle, waiting for someone to ask the right questions. And one of the first people to ask some very big questions was a certain printer from Philadelphia. The story of electricity is filled with brilliant minds, but few are as famous or as charmingly reckless as Benjamin Franklin. In the mid-17th century, while also being a printer, a politician, and a diplomat, Franklin became fascinated by this invisible force that could be stored in a jar. He was particularly obsessed with a big, bold question. Was the tiny, crackling spark from a Leyden jar the same stuff as the immense, terrifying power of lightning? At the time, most people saw lightning as a supernatural force, an act of God, something to be feared but never understood. Franklin suspected it was something much more mundane. He believed it was just electricity, but on a massive planetary scale. And, being a man of action, he decided to prove it. This leads us to one of the most famous, and frankly, most dangerous experiments in the history of science. In 1752, during a thunderstorm, Franklin, assisted by his son, flew a kite with a metal key tied to the string. His idea was that the kite would attract the electric fire from the storm clouds, which would then travel down the wet string to the key. This was, and I really can't stress this enough, an incredibly dangerous thing to do. It's the kind of experiment that should have a large flashing warning label that says, "Please do not try this at home, ever." But Franklin was careful. He stayed dry under a shelter and held the string with a silk ribbon to insulate himself. As the storm clouds passed over, he noticed the loose threads of the kite string standing on end. He then brought his knuckle close to the key, and a spark jumped between them. It was the same kind of spark he could get from a Leyden jar. He had done it. He had proven that lightning was electricity. This was a monumental moment. Franklin had taken one of nature's most terrifying forces and brought it down to earth, showing that it was a natural, understandable phenomenon. But he didn't stop there. He immediately turned this profound discovery into a practical invention that would save countless lives and buildings. The lightning rod, a simple metal rod connected to the ground that could safely channel the immense power of a lightning strike away from a structure. With one daring and slightly crazy experiment, Benjamin Franklin had not only demystified the thunderbolt, but he had also shown the world that this strange invisible force could be tamed and controlled for human benefit. For a while, the study of electricity was all about static shocks and sudden sparks. The next great leap would be to get this invisible force to do something even more remarkable, to flow. And weirdly enough, this discovery was all thanks to a frog. In the 1780s, an Italian physician named Luigi Galvani was conducting experiments on frog legs. As you do. He noticed that when he touched a frog's leg with two different metals, like brass and iron, the leg would twitch and kick as if it was still alive. It was a discovery that was one part brilliant science and one part gothic horror movie. Galvani was convinced he had discovered animal electricity. He believed that life itself was an electrical force, and that this energy was stored in the muscles of the frog. It was a fascinating idea, and it captured the imagination of the public. But another Italian scientist, Alessandro Volta, was not so sure. Volta suspected that the frog was not the source of the electricity, but merely the detector of it. He believed the real magic was happening between the two different metals. This sparked a friendly but intense scientific debate. Was the electricity coming from the animal or from the metals? To prove his point, Volta decided to get rid of the frog altogether. He experimented with stacking discs of two different metals, zinc and copper, and separating them with pieces of cardboard soaked in salt water. When he connected a wire to the top and bottom of this stack, he discovered it produced a steady, continuous flow of electricity. Not a sudden spark, but a current. He had created the voltaic pile. It was, in essence, the world's first battery. It was a clunky, slightly damp, and not very powerful device, but it was one of the most important inventions in human history. It finally untethered electricity from the friction of amber and the fleeting power of lightning. It turned electricity into something that could be produced on demand, something stable, and something that could be put to work. The invisible fire was no longer just a spark to be captured. It was now a river that could be made to flow. The invention of the battery was a complete game changer. For the first time, scientists had a reliable and continuous source of this mysterious electrical fluid. They were no longer just chasing sparks. They had a river to study. And this new tool led to one of the most important discoveries in the history of science. Our story now moves to Denmark in the year 1820 to a lecture hall where a physicist named Hans Christian Ørsted was giving a demonstration. As he connected a wire to a powerful battery, he noticed something strange. A compass sitting on the table nearby, which had been pointing north as a good compass should, suddenly twitched and pointed towards the wire. When he disconnected the battery, the compass needles swung back to north. It was one of those wonderful hang-on-a-minute moments in the history of science. For centuries, electricity and magnetism were thought to be two completely separate, unrelated forces. But Ørsted had stumbled upon a profound secret of the universe. A flowing electric current creates a magnetic field. The two forces were connected. They were partners in an invisible dance. This discovery sent a shockwave through the scientific community. It was a revelation, the first hint of a deeper unity in the laws of nature. Scientists all over Europe began experimenting, trying to understand this strange new connection. But it was a brilliant, self-taught English scientist named Michael Faraday who would take this discovery and, quite literally, change the world with it. Ørsted had shown that electricity could create magnetism. But Faraday, a man who started his career as a bookbinder's apprentice, asked the opposite world-changing question. Could magnetism be used to create electricity? The answer to that question would electrify the planet. The man who picked up the torch of electrical science was, by all accounts, an unlikely hero. Michael Faraday was born into a poor family in London and received only a basic education. He started his career not as a scientist, but as a bookbinder's apprentice. But while binding books, he also read them, devouring every scientific text he could get his hands on. He was a man with a brilliant, curious, and deeply intuitive mind. Faraday became obsessed with the connection between electricity and magnetism. He was convinced that if an electric current could create a magnetic field, then a magnetic field must be able to create an electric current. For years, he tinkered in his laboratory, trying to prove it. Then, in 1831, he devised a simple and elegant experiment. He took a coil of copper wire and connected it to a device that could detect an electric current. Then, he simply moved a bar magnet in and out of the coil. And as he did, the needle on his detector jumped. When the magnet moved, a current flowed. When the magnet was still, the current stopped. It seems so simple to us now, but this was a moment of profound revelation. This was electromagnetic induction. He had found the answer. Magnetism, when in motion relative to a wire, could indeed create electricity. But Faraday didn't stop there. He immediately built a device to put this principle to work. he created a simple copper disc that could be spun between the poles of a powerful magnet. As the disc spun, it generated a small but continuous electric current. This was the world's first dynamo, the first electric generator. It was not a powerful machine. It could not light a city or power a factory, but it was the great-great-grandfather of every power station on Earth. In that simple, spinning copper disc, the modern world was born. Faraday, the bookbinder's apprentice with no formal mathematical training, had, through pure intuition and brilliant experimentation, discovered the secret to generating an endless flow of electricity. He had turned motion into power. With the invention of the electric generator, humanity was like a child who had just been handed the keys to a magical kingdom. We could now create electricity on demand. The next great challenge was, what was the best way to send it to people's homes? This question sparked one of the most famous rivalries in the history of science, the War of the Currents. In one corner, we have the most famous inventor of the age, Thomas Edison. Edison was a brilliant and practical man, a showman who knew how to turn an invention into a business. He championed a system called direct current, or DC. Think of DC as a river, with electricity flowing steadily in one direction. Edison used DC to build the world's first power grids, lighting up small sections of New York City and stunning the world. But DC had one major drawback. It couldn't travel very far. It lost power over long distances, meaning you needed a power station on practically every other street corner. In the other corner, we have a very different kind of genius, Nikola Tesla. Tesla was a visionary, an eccentric, a man who saw the universe in terms of energy and frequency. He championed a different system called alternating current, or AC. Think of AC not as a river, but as a tide, with the electricity rapidly sloshing back and forth. This might seem less intuitive, but AC had a kind of superpower. Its voltage could be easily stepped up with a transformer to travel hundreds of miles with very little power loss, and then stepped down at the other end to be used safely in homes. This set the stage for a great battle. Edison, with his established business, insisted DC was safer. Tesla, with his more elegant and efficient system, argued that AC was the future. It was a battle of ideas, of egos, and of two very different ways to tame the invisible fire. In one corner, the pragmatic inventor, and in the other, the visionary dreamer. The outcome of their rivalry would determine how the entire world would be electrified. So, we have our two great minds, Edison and Tesla, with two very different ideas about how to power the world. How was a winner chosen? As it often happens in history, the debate was settled not just by science, but by a grand and ambitious project, the harnessing of Niagara Falls. Have you ever stood near a great waterfall and felt the immense raw power in the air, the thunderous roar of the water? For centuries, people had dreamed of capturing that power, and in the late 1800s, a plan was made to build the largest hydroelectric power station the world had ever seen. The big question was, which system would it use? This was the ultimate test. Edison's direct current, DC, system was well known, but it simply couldn't transmit power over the long distances required. It would be like trying to shout across a windy canyon. The message would fade before it got very far. Nikola Tesla, on the other hand, had a vision. He saw that his alternating current AC system was perfectly suited for the task. His transformers could step up the voltage to an incredibly high level, allowing the power from the falls to be sent hundreds of miles with very little loss, and then safely step down at its destination for use in homes and factories. After a long and difficult public relations battle, Tesla and his business partner, George Westinghouse, won the contract. They built the great power station at Niagara Falls, and in 1896, with the flip of a switch, the power of the thundering water was sent over 20 miles away to light up the city of Buffalo, New York. It was a triumph. It proved on a grand scale that Tesla's AC system was the future. It was the system that would electrify the world. The war of the currents was over, and the visionary dreamer had won. The modern, interconnected electrical grid that we rely on today was born in the roar of that waterfall. And our phone chargers, thankfully, would not require a personal power station in the backyard. While inventors like Edison and Tesla were battling over how to wire the world, a quiet, thoughtful physicist in Scotland was working on a different kind of puzzle. His name was James Clerk Maxwell, and he wasn't so much an inventor as he was a translator. He wanted to translate the invisible dance between electricity and magnetism into the pure and beautiful language of mathematics. Think of him as the poet of physics. He took all the brilliant, messy, and separate experimental discoveries of people like Faraday and Ørsted and unified them. In the 1860s, he produced a set of just 4 elegant equations that described everything known about electricity and magnetism. It was one of the greatest achievements in the history of science. But his equations did more than just describe what was already known. Like all great poetry, they hinted at a deeper truth. His mathematics predicted the existence of waves of energy that would travel through space. And when Maxwell calculated the speed of these theoretical electromagnetic waves, he found a number that was already very familiar to scientists. He had calculated the speed of light. Can you imagine the feeling of that discovery? The sudden, breathtaking realization? He hadn't set out to study light at all, but his equations proved, with the pure logic of mathematics, that light itself is an electromagnetic wave. This was a moment of profound unification. The electricity that made a frog's leg twitch, the magnetism that guided a compass needle, and the light from a distant star were not separate phenomena. They were all different expressions of the exact same fundamental force. Maxwell didn't build a machine or fly a kite. He simply sat down with a pen and paper and, through pure thought, revealed one of the deepest secrets of the universe. It was the ultimate show-your-work moment in the history of science. And it paved the way for the invention of radio, television, and every form of wireless communication we use today. James Clerk Maxwell's equations were a triumph of theoretical physics. They were beautiful, they were elegant, and they suggested that light, electricity, and magnetism were all part of the same family. But for a while, that's all they were. A brilliant idea on paper. His theory predicted that there should be a whole spectrum of these electromagnetic waves, not just visible light. But where were they? Did they actually exist? It's one thing to write a beautiful poem about the universe. It's another thing to prove it's a true story. The man who provided that proof was a German physicist named Heinrich Hertz. In the 1880s, Hertz set up a clever experiment in his lab. He created a simple circuit that would generate a high-voltage spark between two small metal spheres. According to Maxwell's theory, this spark should create an invisible electromagnetic wave that would travel out into the room. To see if it was there, he built an equally simple detector, a small loop of wire with a tiny gap in it. He turned on his spark transmitter, and then, across the room, a tiny, faint spark jumped across the gap in his detector loop. There were no wires connecting the two. Nothing visible had passed between them. It was an invisible signal, a ripple sent through the very fabric of space itself. Have you ever seen the ripple a boat leaves in the water long after the boat has passed? Hertz had seen the ripple, but he was the first to realize there didn't need to be any water. He had discovered what we now call radio waves. He had found a new kind of light, an invisible part of the rainbow that Maxwell's equations had predicted. In doing so, he proved that Maxwell's beautiful poetry was actually a user's manual for the universe. Hertz didn't see any immediate practical use for his discovery, but he had opened a door that would change humanity forever. He had given us the first key to wireless communication. So, Heinrich Hertz had discovered these amazing invisible waves, but he famously said, "I do not see any useful purpose for them." It's one of those wonderfully short-sighted moments in the history of science, like someone inventing the wheel and declaring, "Well, it's a neat circle, but what are you going to do with it?" Luckily, a young Italian inventor named Guglielmo Marconi read about Hertz's experiments and had a very different reaction. He wasn't just interested, he was obsessed. He saw something that Hertz had missed. What if you could use these invisible waves to send messages through the air without any wires? What if you could create a wireless telegraph? It was a brilliant idea, and Marconi got to work in the attic of his family home. He started small, building his own spark transmitter and a simple detector. First, he managed to ring a bell from across the room. Then, he moved his experiment outside and sent a signal from one end of his garden to the other. With each success, his ambition grew. He sent a signal across a hill, then a few miles, then across the English Channel. But Marconi was dreaming of something much, much bigger. He had a goal that most scientists at the time considered completely impossible. He wanted to send a signal clear across the Atlantic Ocean. Do you see the problem? The Earth is curved. Radio waves, like light waves, travel in straight lines. Everyone assumed that a signal sent from Europe would simply shoot off into space, passing harmlessly over the Americas. It was a logical objection, but Marconi was not a man who was easily discouraged by logic. He was convinced it could be done. The stage was set for the greatest and most ambitious radio experiment ever attempted. The stage was set for Marconi's grand and slightly mad experiment. In December of 1901, on a windswept cliff in Cornwall, England, his team operated a massive transmitter. Meanwhile, over 2,000 miles away in Newfoundland, Canada, Marconi himself stood in a storm, holding onto a kite that was flying his simple receiving antenna. All he was listening for was a single, pre-arranged signal. 3 faint dots in Morse code, the letter S. It was, by all accounts, a ridiculous plan. But Marconi listened, and then, through the static and the howl of the wind, he heard it, a series of 3 incredibly faint, ghostly clicks. He had done it. The signal had crossed the Atlantic. The invisible wave had followed the curve of the Earth. But how? It turns out Marconi had an unknowing and very helpful partner in this experiment: the Earth's upper atmosphere. He had discovered, completely by accident, a layer of electrically charged particles called the ionosphere. This layer acted like a giant curved mirror for radio waves, allowing his signal to bounce between it and the Earth's surface and follow the planet's curve. It was like skipping a stone across a pond, but the pond was the atmosphere, and the stone was an invisible message. That faint 3-dot signal was the birth of global communication. It was the first whisper of the world we live in today, a world of radio, of television, of global connection, a world where distance was no longer a barrier to the human voice. The world had suddenly become a much smaller place. And it was all thanks to a man who refused to believe that a simple curve could get in his way. For all the incredible progress with batteries, generators, and radio waves, scientists at the end of the 19th century were still wrestling with a fundamental question. What is electricity? They could see what it did, but they had no idea what it was. The answer would come not from looking at massive power stations, but from looking at the smallest possible components of matter. At the time, the atom was thought to be the final indivisible building block of the universe, like a tiny, solid billiard ball. But in 1897, an English physicist named J.J. Thomson was experimenting with a strange device called a cathode ray tube, which, funnily enough, is the great-grandfather of your old boxy television set. He was sending a beam of energy through a vacuum and noticed that he could bend and steer this beam with a magnet. This was strange. It meant that whatever the beam was made of, it was not light. It was made of something with a negative electrical charge. Through a series of brilliant experiments, he was able to measure the properties of these tiny somethings. And he came to a stunning conclusion. These particles were almost 2,000 times smaller and lighter than the smallest known atom, hydrogen. He had discovered a fundamental subatomic particle. He had discovered the electron. It was the first subatomic particle ever found, the ghost in the machine that made everything work. Thomson realized that these tiny electrons were a universal component of all matter. It turns out the river of electricity wasn't some magical, invisible fluid after all. It was a stampede of incredibly tiny, negatively charged things, flowing from atom to atom. It was a discovery that would open the door to a whole new level of reality the quantum world, and would finally give a face to the invisible fire. We've spent a lot of time in the dusty, candle-lit laboratories of the 18th and 19th centuries, with strange glass jars and twitching frog legs. But what does all of that have to do with you, right now, as you're listening to this? Well, everything. In fact, you are probably holding the entire history of our story in the palm of your hand. Let's talk about your smartphone. That little slab of glass and metal is a miracle of modern engineering, but it's built entirely on the discoveries of those patient, long-dead scientists. The battery that powers it? It's the great-great-great-grandchild of Alessandro Volta's simple pile of metal and salty cardboard. So, next time you're desperately looking for a charger, you can send your thanks, or maybe your complaints, directly back to him. Do you have wireless charging? That little bit of magic that happens when you place your phone on a charging pad, no plugs involved? That's pure 100% Michael Faraday. It's his principle of electromagnetic induction, the same one he discovered by moving a magnet through a coil of wire, now miniaturized and working silently on your nightstand. And how are you listening to this right now? Probably through Wi-Fi or a mobile signal. Those are just different flavors of the same electromagnetic waves that James Clerk Maxwell predicted with his 4 beautiful equations. He proved that light, magnetism, and electricity were all connected. Think about that for a second. The same fundamental rule of the universe allows you to stream this video and allows light from a star 1,000,000 light-years away to reach your eyes. And the phone itself, the processor, the memory, the screen, it's all powered by our ability to control the flow of those tiny ghosts in the machine that J.J. Thomson discovered, the electrons. The entire digital world is built on shuffling around trillions of those little subatomic particles. Every time you send a text, you are using the legacy of Marconi. Every time you take a picture, you are using a descendant of Einstein's photoelectric effect. You are holding a device that is a direct conversation with 2 centuries of human curiosity. It's not just a phone. It's a lightning rod, a Leyden jar, a battery, and a radio transmitter, all squeezed down into a shape that fits in your pocket. For a century, our world has been powered by a rather dramatic and noisy process: burning things. We've been like cavemen who discovered fire and then just kept making bigger and bigger fires. It's been incredibly effective, but it's also been a bit messy. Now, we are in the middle of a slow, quiet, and incredibly profound shift. We are learning to get our power not from burning, but from the gentle, constant forces of the planet itself. We are returning to the original power source, the sun. Isn't it a beautiful thought? The same photoelectric effect that a young Albert Einstein used to prove that light was a particle is now being used in every solar panel across the globe. These silent, dark rectangles are the direct descendants of his thought experiment. They are catching photons that have traveled 93 million miles from the sun, and, with a quiet bit of quantum magic, turning that light directly into an electric current. There are no moving parts, no noise, no smoke. It is the most peaceful revolution in the history of energy. And it's not just the sun. we are also learning to listen to the wind. Have you ever seen one of those giant, graceful wind turbines turning slowly on a distant hillside? They look serene, almost lazy, but they are giants of immense power. Each one is a direct descendant of Michael Faraday's simple spinning copper disc. They are using the gentle, invisible movement of the air to turn a massive generator, transforming motion into clean, quiet power. What we are witnessing is a fundamental change in our relationship with electricity. We are moving away from the loud, centralized model of a few giant power stations and towards a softer, more distributed world, where power is generated quietly, locally, by the sun on our roofs and the wind in our fields. It is a slow and patient transformation, but it is a powerful one. For a very long time, our electrical grid has worked like a one-way street. A giant power station at one end creates the power, and it flows outwards to our homes. It's a simple and effective system, but not a very clever one. But what happens when you have power coming from millions of different places? From every solar panel on every roof and every wind turbine in every field. You need a new kind of grid. You need a brain. This is the quiet, digital revolution of the smart grid. The idea is to transform our old one-way electrical system into an intelligent two-way conversation. It's a web of power woven together with sensors, computers, and artificial intelligence that can manage the flow of electricity with incredible precision. Think of the old grid like a simple garden hose. You turn it on at one end and water comes out the other. A smart grid is more like a sophisticated, automated irrigation system for an entire country, with computers that know exactly which plant needs water and when, ensuring that not a single drop is wasted. In this future, the grid won't just send you power, it will talk to you. It will know the best times to charge your electric car when energy is cheapest and most abundant. Your own home, if it has solar panels, might sell its excess power back to the grid, becoming a tiny power station of its own. Have you ever thought of your house as a potential power plant? It's a strange but wonderful idea, right? The goal of the smart grid is to create a system that is more resilient, more efficient, and far less wasteful. It is the invisible, intelligent nervous system that will allow our clean energy future to truly shine. We have explored the gentle power of the sun and the wind and the intelligent web of the smart grid. But there is one final, almost mythical source of energy that scientists have been dreaming of for a century. The power that is locked away inside the atom itself. This is the world of nuclear energy. The kind we have today, called nuclear fission, is a process of splitting heavy atoms, like uranium, to release an incredible amount of energy from a very small amount of fuel. It is a powerful but complex technology, a quiet giant that generates a huge amount of our electricity without producing any greenhouse gases. But what is the ultimate dream of electricity? It's not just about building better solar panels or splitting atoms. It's about building our own tiny, well-behaved star right here on Earth. Sounds like science fiction, doesn't it? Well, it is, for now. But we're getting closer. This is the dream of nuclear fusion. Fusion is the opposite of fission. Instead of splitting heavy atoms apart, it involves fusing light atoms, like hydrogen, together. This is the very same process that powers our sun and every other star in the universe. It releases even more energy than fission, and its fuel, hydrogen, can be found in ordinary water. The best part? It produces no long-lived radioactive waste. The challenge, and it's a big one, is that to get atoms to fuse, you need to create conditions of immense heat and pressure, hotter than the center of the sun. It's like trying to bottle a star. It is one of the most difficult engineering challenges humanity has ever undertaken. But if we can solve it, it would be the final chapter in our long journey. It would be a source of clean, safe, and nearly limitless energy. It would be the moment we finally and truly brought the fire of the stars down to Earth. We have journeyed from a simple piece of amber rubbed with wool to the very heart of a star. We've seen this invisible force move from a magical curiosity to the silent, steady servant that powers our entire world. It's a story of quiet observation, brilliant ideas, and the patient human desire to understand the universe. Isn't it a comforting thought? That this force is not something loud or chaotic, but a gentle, fundamental rhythm of the cosmos. It is in the soft glow of your lamp, the connection to this video, and the tiny electrical sparks that are carrying these words from your ears to your brain. It is the quiet hum of a world at work. From the grandest galaxy to the smallest atom, everything is connected by this invisible energy. And that brings us to the end of this video. If you are still awake, I'd like to thank you for being here with me as we travel these science journeys together. It brings me great pleasure to create these stories and bring them to you, and I truly hope it has given you some relaxation, even just a little. If it sent you off to sleep, well, then that is job done. I'd really appreciate it if you could think about clicking the subscribe button and liking the video. Even just dropping a comment below on where you are in the world and what time it is helps the channel grow and allows me to make more content for you in the future. Now, I hope you drift off to sleep if you haven't already. For anyone wanting to still drift off, you are welcome to listen to the ambient sounds that will follow. Thank you again for sharing your time with me. Sleep well, and may you all have sweet dreams. Until the next time, good night.